Yes, so this is the first of 3 lectures, and I didn't know what level to pitch it at. So you can please shout if it's too easy, too difficult, and maybe in the discussion session you can tell me, ask more questions, or tell me to speed up or slow down. Yeah, so Hermitian K-theory, or, well, higher Grothendieck Witt groups is a version of algebraic K-theory that takes into account dualities. Okay, so let's define. Usually I just stick to commutative rings, but I think in the audience we have people who do versions of that for rings with involutions, so let's start with that. Okay, I need to get this. A ring with involution. So this is a ring R together with a ring isomorphism to its dual, such that if you compose it twice, you get the identity, I guess. So I may call that. So and typical examples are, well, if R is commutative, then you can just take the identity. Or if R is, for instance, somehow like a group ring, you can take an involution sending an element of your group to its inverse. I'm going to use notation throughout, which is going to be some mod R, mod where the R is left, right on both sides. There's going to be right R modules, left R modules, and bi modules. Should be clear from the definition. And I use R proj for finitely generated left projective left R modules. So usually, the goal is for today at least define a space and whose homotopy groups are going to be the higher Hermitian K groups, or higher Grothendieck Witt groups, and but it depends on some coefficient system, which I'll go put in here. So I have to define what that means. So I write it down in a way that it makes sense for DG categories, for instance, or differential graded algebras, because that will be useful later. So a coefficient module is going to be a bimodule L, so together with a bimodule map. Oh, I need to introduce the notation, another notation. So notation. If M is a right module, or a left module, or a bimodule, then I'm going to write M op for another module. It's going to be changing. It's going to be left module, right module, or again a bimodule, where I just use the duality on my ring R to switch left and right modules. So, for instance, I guess I want to make I start with a right module, and now I want to make a left module. So it's going to be the same underlying a Being group. And the multiplication now, I guess, if I start with the right module, I want to make a left module. I just use the involution on R to define the multiplication AX goes to X A bar. Okay, so that's our left. And similarly, you have definitions here. So in this sense, coefficient module is going to, for our Grothendieck space we're going to define, is going to be a bimodule together with a sort of involution on the bimodule. So it's a bimodule map such that, again, sigma is the identity. This is actually an isomorphism. So maybe write an L here, and for R, it's going to have an index R there. Well, and usually we want something more, such that, because we want to define a duality, use that to define a duality on the category of R modules, projective left R modules. So, and usually I will denote, so I said it already here, so the bar, usually sigma of x is just sometimes denoted x bar for a shorter notation. Okay, so we also require sometimes that, so if P is a finally generated projective left R module, we want to define a dual. Now it depends on L as maps into L. Well, it's going to have to be a left module. So, but this is a bimodule. So if I stick P in here, make it to a right module, and take right module homomorphism, then what I still have left is a left module, because this was a bimodule. So this is, so we require that. So this is automatically a left module anyway. We require this to be projective left module. And two, we also want that the map, so there's a canonical map to its W, which is you send every x to, there's a homomorphism from homomorphism to L, so you can evaluate at x, but that will not do the trick, so because it's not going to be in the set, so you have to compose with the duality on L. So this is, the sense, it's a map from hom P up, L to L, sending some function f to, you evaluate at f, at x, and take then bar, right? With the convention that this is the, this is sigma here. So, and we require that this is, that all depends on the context, but the context now is projective modules, so we require this map to be an isomorphism for all projective left R modules. I'm not quite understanding your question. Yeah. Yeah. So, I mean, if you stick in R itself, then, L is going to be, in this context, it's going to be projective, finally degenerate projective, both left and right modules. But, I mean, it's written down in a way that you can actually apply DG algebras. Okay? And all of this makes sense in the world of DG categories. Okay? And then L does not need to be projective or even can be an injective resolution of something, or just an injective complex. We require the strict condition. The only things we will relax is isomorphism. Going to relax isomorphism to quasi-isomorphism, but otherwise it's the same. Does this answer the question? I'm not sure who would answer. I don't claim that is the case. I mean, eventually we'll talk about categories of duality, and that will have all duality structures in it. That's right. No. It depends on the sorry. It depends on what you stick in. Okay, you replace. I mean, we're running ahead, but so you stick your. So you decide what the category of duality is supposed to be. Here we decided it's going to be projective R modules. Okay, and then we want the duality, of course, to preserve that category. So now in a DG world, you can take complexes with coherent cohomology. Okay. Then that L will be some complex which has these two properties, 1 and 2. One says that the duality defined like that stays has image in your category you're interested in, and the second one says that, well, in this case you want to replace isomorphism by quasi-isomorphism. But then the rest is just taken in a categorical or symmetric monodal, or close symmetric monodal sense. But since this, we're gonna I guess sometimes, specialists sort of know that sometimes one has an epsilon somewhere, but that epsilon is in the multiple in the coefficient module. You can change sigma L by some multiple. Okay, so yeah. So for instance, you can always take example. You can always take if R is a ring with involution, then you can take L equal R and sigma L to be the duality of that. But you can also take, when R is commutative, you can take sigma equal, for instance, the identity, and you can take L to be any line bundle, and for instance, then sigma also the identity. Okay, so now the main object of study is inner product spaces. Is over. So the pair ring with involution together with coefficient module L is in our case it's going to be, I guess, a finitely generated projective R modules module together with a map of bimodules, call it maybe P, map of bimodules. See, P is the left R module, P op is the right R module, so this is a bimodule. I require this to be a map of bimodules, okay? Such that two things happen. First of all, it's symmetric, so I have the symmetry map. So if you look where it really goes to, it goes to this. This is a bimodal homomorphism, actually bimodal isomorphism. And this is bimodal isomorphism for this bimodal structure. Written there, okay. And then you see that you have to take here phi op, which lends an L op, and that's required to commute. So, yeah. For instance, if you're in a commutative situation and this is just multiplication by -1, then you see skew symmetric forms. If you're in a commutative situation and this is the identity and this is just R, then you have symmetric forms. And we require that the map from so we have P to its dual. We call this the sum of right R modules from P op to L. There was phi hat x goes to phi of x comma blank. be an isomorphism. Again, so this is also what it means, for instance, if you're in a DG world, what it means to be an inner product space in a DG world. This is now complex, well, depending on which category you're looking at, either, say, complex of projective modules, or complex of vector bundles, or complex of quasi-coherent sheaves with coherent cohomology. Okay. Well, this makes sense. This is also a map of bimodules, but not of DG modules, such that this commutes. That's what it is, together with this one now not being an isomorphism, but a quasi-isomorphism. That's the only difference. But anyway. So this is an inner product space. And now so anyway, another point about this is in our definition there's no choice of any sign when you do complexes. Everything is defined given the symmetric monodal or close symmetric monodal structure. No, depending on the context. For instance, if sigma is -1 and you're over a local ring, commutative, then you talk about symplectic modules, and they all have even rank, for instance. Okay, do you want examples? Yes, example. Yeah, okay. So, yeah, I'm sure there are specials. I don't know. Yeah. How about discussing that in discussion session? I mean, okay. So you wanted non-examples, so can I erase that? What else? Yes. Anyway, so if I give well, this condition here, I mean, to give the sort of bilinear form phi is equivalent to giving the map phi hat. And one way is defined by phi. And then one commutes if and only if the map so you have phi hat and yes, so we assume, so we do. Well, it's equivalent to saying that that is the same as if I apply the delta to that. So then I go from P upper star to that, and then here's the canonical isomorphism. So you check, so the exercise that one commutes if and only if that commutes. Okay, so it's non-isometry of inner product spaces. Is, well, so from x phi to y comma psi to inner product is an isomorphism x to y iso such that the form of phi restricts to the form of, well, the form psi restricts to f such that the phi is psi f dual. Okay. So that's an isometry, and so this defines a category, actually a symmetric monoidal category inner product spaces. So of inner product spaces over that with a modular structure given by a direct sum or orthogonal sum. X, phi, y, psi is by definition x plus y. And now I'm identifying phi and its hat, so I'm not going to write this anymore, phi, with the map to its dual. Okay, so now, so this is a symmetric monoidal category, and to any symmetric monoidal category you have associated K-theory, and the K-theory associated to this symmetric monoidal category is going to be the Grothendieck space. So let's recall what that means.
Sorry, the definition of an isometry with a product space is the phi and psi, is that when you're using the perspective of them, like
The hats. Yeah.
Okay.
So I'm not going to. Yeah. Okay, so eventually I will drop the hats, but maybe I'll keep them for a moment. I mean, the 2 points of view are completely equivalent, and so I will eventually drop that. Okay, so let's recall what's the K-theory of a symmetric monoidal category. So let S be a symmetric monoidal category. So it comes equipped with some symmetric monoidal product, and let's say a unit, which I denote 0. And S is called group complete if pi naught is a group. If pi naught S, well, is a group, where pi naught is, well, you take the nerve and the topological realization of the category, then you get an H space, and that's in this sense. Or alternatively, pi naught is just the equivalence classes of objects in here, where you declare 2 objects equivalent if there's an arrow between them, and that generates some equivalence relation. So now, again, so this is what this means to be group complete, and let now S be any symmetric monoidal category, then a group completion of S is a symmetric monoidal category. Well, denoted, let's say, S minus 1S together with a monoidal map of functor from S to S minus 1S, such that into a, well, group complete symmetric monoidal category, such that, well, On homology, it has the following effect. Where you have a map on homology, and well, this is a pi naught z. So this is an abelian monoid, so this is a ring, and this thing is a module over that ring, and this is a commutative ring. It's a module over that commutative ring, so I can localize at any multiplicative subset. And so, well, the action of the translation of adding an object here is a weak equivalence because it's group complete, and therefore this map factors through that map, and the requirement is that this is an isomorphism. So that's a group completion, and the remark is, I think it doesn't matter. Yeah, constant coefficient. Yeah. I mean, you can take a local system. That's what's usually stated, but I mean, the remark I'm going to make, yes, because I mean, there's a functorial way of doing that, and any group completion between group complete symmetric monoid categories is a weak equivalence. There's a functorial way to associate to any symmetric monoid category a group completion, a group, of it together with, I mean, a group completion of it. No, but that's a model. That's a model. What you're telling me is that's remark number 2. You're telling me no. So, if is faithful, then Quinn gives the model. Gives a model for S minus 1 S. Okay. But I mean, Thomason gives you a model for any symmetric monoid category. Okay. That's depends on what you well, one way of saying you take if you know about the topological realization of a category, classifying space, then we take the homology of that classifying space, and I always, when I don't write any coefficient, it just means that coefficient, okay? Is that okay?
Yeah.
Good. It's also some derived functor for modules over C, but okay. And remark 1 is that the group completion is unique in a certain sense, which you can ask me about. I mean, I explained that. So, group completion is unique. Well, I mean, yeah. I'll say what it means. Any group completion between group complete H spaces, group complete symmetric monoid categories is a weak equivalence. Okay. And if you have, and there's a functor that sends symmetric monoid categories to group complete ones, and that's a group completion. And so if you have any group completion, you can compare it with the preferred one, which is the functor. And it's going to be weak equivalent by its very definition. So we can speak of V if you want. And since I don't want to give an explicit, I mean, maybe most of you or some of you are familiar with equivalence construction, so that's good enough for what we do. Yeah?
So Thomason has a paper I haven't read, but I know it's called Beware the Phony Multiplication on Closed Nested.
That's right.
So are there like hidden substitutes there, or is that?
That's about when we talk about ring structure or multiplication. It's not about the making something into a group complete H space. Huh? Yes, if you want to make the resulting, But the K-theory of a symmetric monoid category into a ring, if you have extra structure like a tensor product, then using the naive way on S minus 1S is not going to work. That's the paper. So, anyway, so this allows us to define now the Hermitian K-theory space. Yes, okay, unique. So there exists a functor. Let me still call it S minus 1. Is that okay? Even though that's not equivalence. Together with natural transformation, monoidal natural transformation, which is a group completion. Okay, so this is Thomason. So then B, if S2T is a group completion, then we get a diagram S T S minus 1 S, let's call it then T minus 1 T. Okay, all arrows are group completions. And so, and on homology, you get this diagram. Okay. Now, saying that these things are group homology, so I invert the action of pi naught. And then I have isomorphism here, isomorphism here because it's already group complete, and I have isomorphism here then. Okay, so I have a homology isomorphism between group complete H spaces. So this implies that S minus 1 S to T minus 1 T and T, they're all weak equivalences. So in the homotopy category of I don't know, associated infinite loop spaces, these two things are the same. Does this answer your question? Okay. So, yeah, so that means to some extent we don't need to worry. And anything that's functorial for whatever you want to do is good enough. So then let's define the Grothendieck-Witt space as, the topological realization, but I'm not going to write this. The category of inner product spaces, S minus 1 S, where S is the category of inner product spaces with isometries as morphisms. So, okay, and then the first lemma, in fact, it's by definition actually that the Grothendieck-Witt group that I've defined at the beginning is the same as pi naught of the space. And then one defines the higher groups as the homotopy groups of the space. Okay. So, yep. Well, and of course the goal is to compute these things and see what they have to do with lots of other things. They come up in A1 homotopy theory, they come up in computation of obstruction groups for no vanishing sections of vector bundles, and yeah. That's the group that I defined at the beginning, that I've denoted like that. That's the... Did I define it? Oh. Huh? Oh, and I jumped ahead. Where? I guess okay. Where? Well, okay. This is the same as the free abelian group on isometry classes of inner product spaces. Isometry classes of inner product spaces over this pair. Modulo edit the fact that X, well, if I have an inner product space, orthogonal sum is the same as the sum in. Okay. Yeah, I mean, I'll come to that at some point, but at this point, it's yeah. I mean, so you ask me, okay, so in yeah, it is true, yeah. So it's a dilemma, but I mean, just when you say what you say, yes, if a form has a Lagrangian, then that Lagrangian means a subspace, admissible subspace, which is its own orthogonal. Then in that group, it's equal to the hyperbolic associated to the Lagrangian, whereas the space itself may not be isometric to the hyperbolic of the Lagrangian. Okay, but in that group, it is equal to, yeah.
What is the difference between group completion of the symmetric category and the K-theory of such a category?
That's the same.
It's the same.
That's right. Yeah, so I introduced that by saying the Grothendieck space is the K-theory of the symmetric monoidentity of inner product spaces. That's right. That depends on your level of generality of what K-theory is. Okay, that's what it is. Yep, so it's just K-theory. Now we have said what GW0 is, so I can give some examples, which I intended to give anyway. So if R is commutative, say, and coefficient system, so is R, and so all the dualities are trivial, say. Then, for instance, so then we just write GW0R for GW of this pair, 0 or not. Let me write an I here. And there are classical computations, which I want to recall. So, for instance, the Grothendieck group. I mean, if all of this is, maybe I shouldn't waste my time, I'm not sure. This is an isomorphism, and this is just Z plus Z, sending an inner product space V to rank of its positive definite part, comma, rank of its negative definite part. The Grothendieck group of a finite field is just Z plus units mod square units, sending what's the map given by rank and determinant, F finite field, and another famous example is the Grothendieck group of the rational numbers. That's the same as Grothendieck group of the real numbers, 2 copies plus direct sum over the primes of the Witt groups of the finite fields, where the Witt group is just the Grothendieck group modulo hyperbolics, where for projective module, the hyperbolic module, well, depends of course on the coefficient system, is P plus its dual together with the form, that's 1, and the canonical identification with its double dual. So this is called hyperbolic module of P. Okay, so these computations are completely classical, but the way of writing it down like that, well, it's completely independent of characteristic, and yeah, that's a way of writing it down. So here's a comment that follows from the definition. So it's going back to the definition as what I've erased now, as the group. Right. So we know the homology. Right. So the homology of the Grothendieck space is just the homology of inner product spaces, and you invert well, isometry classes of inner product spaces. So from that you get the following. So as in K-theory, you well, if you know what K-theory is, so if I denote by GW greater or equal to 0 the connected component of the space GW at the base point 0, so this is the 0 object, then, well, for K-theory you know that the connected component of K-theory is VGL plus. And you want to say something like that here, but the argument uses that you have a cofinal family. Okay, so, and in general you don't have a cofinal family, but under this hypothesis you do. If 2 is invertible, then Hn is cofinal in the category of inner product spaces. So that means that for every inner product space, there exists another one such that the direct orthogonal sum is isometric to hyperbolic of Rn. Okay, and so that allows you to enter, well, if you denote On of R maybe comma L as the automorphisms of that hyperbolic space, then it is inside the next one, sending an automorphism to automorphism plus identity on hyperbolic of R, and then you can take the union, and that's the infinite orthogonal group. Then O infinity R L, it's the union of these guys, and then under this hypothesis, simply using this that there's a homology isomorphism between the classifying space of O infinity and the homology of the connected component at 1, or at 0. And so this implies that, well, you can think of the connected component as just BO infinity plus of R. Okay. But again, that's under this hypothesis here. But only there's just definition. It just follows immediately from definition. There's no deep mathematics going on here. So without this hypothesis in general, I don't think there's a nice description. I mean, one can construct some gigantic group which serves that purpose, but I don't know if that is of any help. Very much. Okay. So, well, in order to do anything more, one needs to generalize the concept. So, well, let's see. How far will we? Between quadratic forms and symmetric binary forms. But I'm not talking about quadratic forms, yeah. I mean, yeah. So anyway, maybe one more remark before I try to go more general. So if R is the ring A cross A op, so A is any ring, and with the duality by the involution, switching the two factors, then in fact the category of inner product spaces of that ring with duality, so and I'll take L to be coefficient system, just the ring itself with the same involution, then the category of inner product spaces is just equivalent to the category of finitely general projective R modules. And so that tells you that in this case the Grothendieck space is just the same as the K-theory space of A. It's also immediate from definition. That's all. Okay, so now to prove anything more deep, we need to generalize definition. So now you can follow Quillen's program, define it for exact categories, and that has been done some time ago. But then you'll find out, and then there's a Q construction, or Hermitian Q construction, which is useful to prove some result, but you don't get as far as, by far not as far as Quillen did go with his Q construction and to prove theorems. So maybe to make things slightly shorter, I'm going to define a slightly more general notion, exact category with weak occurrences and duality. Let me say that. An exact category with weak equivalences and duality is, so a quadruple E, W, star, and some map can, where, so E is an exact category, So, I mean, in short, it's an additive category plus a notion of short exact sequences. Satisfying a list of axioms, but they're equivalent to saying that E is a fully faithful subcategory of some abelian category in such a way that sequences, which is extension closed in the abelian category, and such that a sequence in E is exact if and only if its image in the abelian category is exact. Okay, so that's one way of shortly saying what an exact category is. So omega, actually, sometimes also written omega E as a category. Anyway, it's a set of morphisms of E satisfying some assumptions. For instance, all isomorphisms. So they're called weak equivalences. So all isomorphisms are supposed to be weak equivalences. So weak equivalences are closed under various operations, isomorphisms, retracts, push outs along admissible monomorphisms. These are the injections in short exact sequences. Pullbacks along admissible epimorphisms, and has this 2 out of 3 property, property. I guess if 2 composable maps F and G are given, if any 2 of F, G, and their composition is a weak equivalence, then the third one is 2. Okay, so that's weak equivalences. Then so then we have the duality. So far, what I would call that an exact category with weak equivalences. Now, so I've explained W star is an exact functor. Functor such that, it sends weak equivalences into weak equivalences. It's a can is a natural transformation from the identity to the W identification. So star composed with star, such that, so it's a natural transformation, such that, it's a weak equivalence for every object. X to X star star is a weak equivalence, and the following diagram strictly commutes when, so you have a dual, so you have a canonical double identification for X star, but you can also take the dual of X, the canonical double identification here, and you get back to X star. And so that's diagram is supposed to commute. So I think that is it. That's right. So examples. So I guess I have a few more minutes, maybe. Yeah. So, yeah. As before, if R and L are the ring with involution, L is some coefficient system, then you have the category of finitely generated projective R modules. Well, you have the as weak equivalences, just the isomorphisms. Then you take as the dual, is the dual that I've defined before, right? Some right R modules from opposite to L, and I defined for you the canonical W identification. Another example is if X is a scheme and a line bundle, then you can take vector bundles on X. So with its natural exact structure as a subcategory of quasi-coherent sheaves on X, you can take isomorphisms and then the duality just hom into L, and then there's also canonical W identification, always defined in this. The canonical W identification is always defined in the same way because it's, as I did in this case here, because it just has to do with the closed symmetric model structure that we're talking about. So this, yeah. So for instance, now we can also take vector bundles, complexes of vector bounded complexes of vector bundles. Again, now as weak equivalences quasi-isomorphisms and as duality hom, and now you're actually free to take any shift of a line bundle, and then again it has a canonical double identification, just coming from the symmetric model structure on vector bundles. This generalizes to any, so for instance, any, you can take the category of bounded chain complexes in an exact category. So if E is I star can is an exact category with duality where the weak equivalents are isomorphisms, you can always construct a new one, just a chain complexes, and then here there's a notion of quasi-isomorphisms and star induced morphism and can. And you can also take just complexes of quasi-coherent modules with coherent cohomology if X is Noetherian. And then you have quasi-isomorphism, and then you can take as duality hom into some dualizing complex. And then there's again a canonical double identification. So X. So there are lots of examples that fit the framework. Yes. So and the goal is to define a Grothendieck space or spectrum in this for such guys. Yeah. So how much time do I have? Okay. So then I'll stop and I'll give the definition tomorrow. Okay. That depends on what you, I mean, I can write down any definition.
You need it for something like approximation theory.
Okay.
How far is this from a full model to the infinity categorical notion of the category, of an exact category with duality?
I know you have specialists here. You ask them.
I think it was price or such a thing, but I don't know how. It's a little bit more strict, I would say. Yes,
I mean, one of the main points has been, yeah, as long as possible, I would like to not assume two invertible and see how far I can go with that.